So that was a discussion about vaporization and condensation, changing between gases and liquids. And my computer's unhappy. So now we're going to talk about the transition between solid and liquid, or solid and gas. When we have a solid and we increase the temperature, the increasing thermal energy causes the molecules and atoms to vibrate faster. And when we reach the melting point, they have enough thermal energy to overcome those forces that are holding them stationary. They're still going to be held together because as they break the one force, another forms with somebody down the line. But they're able to move about, and this is why liquids act liquidy, right? They pour and they take on the shape of their container because the molecules can slide around relative to each other. So here we have an illustration of water in the solid state. We call it ice. And it is held rigidly in these open crystalline lattices. And as you heat it up, the molecules vibrate enough that they can break loose from that. And in the liquid, they're just kind of swimming around. They're milling about. And just like with the boiling, when we have that transition between states, we see a constant temperature. A mixture of water and ice is always going to have a temperature of 0 degrees Celsius at 1 atmosphere of pressure. And it's only after all the ice has melted that the temperature will rise again. And so another one of these heating curves, this one's starting out lower. We're adding heat to ice, minus 20 degrees. We add heat to it, the ice warms up. When it gets to the melting point at 0 degrees, all of that heat that's being added goes into that transition from solid to liquid. And there's no increase in temperature until all of the solid has melted. And then, when it's all melted, then the water will increase in temperature until we get up to the boiling point. Then we would see another flat place. So adding ice to your beverage cools it because melting is an endothermic process. Holding an ice cube in your hand, you feel the heat leaving your hand. That's why it feels cold, because heat is flowing from your hand to the ice cube. It's endothermic. So if melting is endothermic, then freezing must be exothermic. And again, that's the transition that's not so obvious. When something freezes, it gives off heat. Well, usually what we experience is that to make something freeze, you have to take heat away from it. And that's what your freezer does. It's pulling heat out of the inside of the freezer so that the water will freeze. Freezing is an exothermic process. And this is the principle that makes watering the orange trees during a freeze useful. Because as the water that you've put on the fields freezes, it actually releases energy and moderates the temperature so that the temperature in the orchard doesn't go down farther. Sorry for the beeping thermostat interruption there. Okay, so I guess we're done with that one. So heat of fusion. Fusion is also a word for melting. If you think of putting solid chocolate chips in a pan and warming them up, they fuse together as they melt, right? That's how I remember that fusion is melting. So the heat of fusion is the amount of heat needed to melt 1 mole of a solid. So here's the heat of fusion for water. It's 6.02 kilojoules, and that's going to melt 1 mole of solid water. That delta H is positive because it's an endothermic process. We can also have the reverse of freezing the liquid. The number is the same, it's just that the energy is moving in the opposite direction. So here the delta H is negative because freezing is exothermic, it gives off energy. So just like we did with vaporization, we can use the heat of fusion to calculate the amount of heat energy required to melt a given amount of solid, and that heat of fusion is used as a conversion factor, giving us a relationship between moles and amount of energy, usually in joules or kilojoules. So calculate the amount of heat absorbed when a 15.5 gram ice cube melts at 0 degrees Celsius. So let's go back and refresh our memory on that number, 6.02 kilojoules. So we need that number. The heat of fusion of water. Yeah, my iPad is just, I don't know. Oh, it's pink now. Okay. Heat of fusion of water is 6.02 kilojoules per mole. That wasn't given in the problem. You have to look it up. So on an exam, if you need that, I'll either provide it in the problem or I'll give you a table where you can look it up. The amount of heat absorbed when a 15.5 gram ice cube melts. Okay, there's not an equation for these problems. It's dimensional analysis. We've got mass, and we want to get to kilojoules. This relationship relates kilojoules and moles. So we need to go from grams to moles to kilojoules. So 15.5 grams of water. We're going to have two fractions. We're going to have moles here and kilojoules there, because this is our path. This is Dora trying to get to the snowy mountains. And you start at the grams, and then you go to the moles, and then you get to the kilojoules. And so here we've got grams to moles to kilojoules. Put grams on the bottom and moles on the bottom. So these guys cancel out. So if you're still iffy on this whole scientific not scientific notation, I don't remember what it's called, dimensional analysis. If you're still iffy on the whole dimensional analysis thing, there's still a great deal of benefit to figuring it out. So if you need help with it, I'd be happy to help you. So you may be understanding now why I have the molar mass of water memorized, because I've used it so many times. We already calculated it once today. So that's the molar mass. And then over here, 6.02 kilojoules per mole. Common mistake students make is that they put the number with the wrong unit, either because they just feel like dividing or I don't know. Make sure it's with the same unit that it came in with. So 15.5 divided by 18.02 times 6.02, and that is 5.18 kilojoules of energy. Any questions? Same thing as with the evaporation. Exact same thing. You do need to be a little bit familiar with this whole heating curve business. And one of the ways that questions can get asked on an exam is to ask you to identify the different sections. So here we've got a flat place at 0 degrees Celsius. What's happening there? The water is going from solid to liquid. So here we've got solid water and liquid water, and it's melting. And what's going on here in this flat spot? We've got boiling. Okay, so here we have both liquid and gas present. And in this section here, we've just got water heating up. So this is going to be liquid. This part down here below the freezing point is going to be a solid. And this bit up here is going to be a gas. So this one's showing the whole thing, going from water at minus 25, we heat it up, it gets to 0, it melts. Once it's finished melting, the temperature will rise. We've got a liquid heating up, gets to the boiling point, starts to boil, the temperature remains constant until it's all boiled to the gas state, and then the gas will heat up farther. We can calculate, like say we had 100 grams of ice, we could calculate how much energy it would take to get it to 125 degrees. but there's going to be a separate equation for each line, and you add them together. So the ones we learned today were this I here and this I. And maybe you're thinking, I. It was the heat of vaporization and the heat of fusion? Or these flat places?
That whole process, what is that?
This is a heating curve. It's called a heating curve. And these slanty parts we learned how to do a while ago. That's the MC delta T, the specific heat capacity. The specific heat capacity of ice and liquid water and steam, the gas state, are slightly different. And that's why their slopes are different. Sublimation is a cool thing. That's when we get something changing directly from a solid state to a gas state. And it's not common, but it does happen. So when a substance sublimes, molecules are leaving the surface of the solid and becoming gaseous. And carbon dioxide is something that does this. We know it as dry ice. We call it dry ice because it doesn't melt, right? It doesn't melt and get the bottom of your cooler all wet. It just goes directly into the gas state. But then you also don't want to keep dry ice in an airtight container because it will explode, as my husband discovered as a child. Well, people do, yeah. It's dangerous. It's really dangerous. Yeah.
With his kid, and he compressed it so that there was no, I mean, it was airtight, and all of a sudden, boom,
Yeah.
I mean, it's just, yeah. No, it's actually really dangerous in a house.
Survival of the fittest. You've heard of the Darwin Awards?
It was
yeah.
Yeah,
and with your kids, it's really bad idea. Dry ice is really fun stuff, but it is dangerous. I mean, you can burn yourself with it. It's like a freezer burn. Anyway, dry ice, carbon dioxide sublimes. It will not melt under atmospheric pressure. You have to actually mess with it to make it melt. At minus 78 degrees Celsius, the carbon dioxide molecules have enough energy to leave the surface and become a gas. That's pretty crazy. Whoops. So here you see the dry ice, and what we see here is carbon dioxide that it's so cold. So what we're seeing here is not the carbon dioxide gas. What we're seeing here is water vapor from the air that is condensing because it's so cold here. But the dry ice will just disappear and not leave a puddle or anything. Regular ice also sublimes. Have you ever noticed if you leave ice cubes in your freezer for a really long time that they get smaller? My kids were watching Arthur the other day, and there's this episode with DW, and she had a snowball in the freezer. And she was so furious with Arthur because he stole her snowball. Because, right? Where's the snowball? Nobody stole the snowball. It's sublimed. So, even in a freezer, in cold climates like Minnesota where my parents live, the ice or snow will gradually disappear because it sublimes. And this is why your food gets freezer burn. And have you ever opened like a package of tater tots or something that you've had for a while? And you're like, here's the tater tots, and then there's all these ice crystals. I'm like, why did they put ice crystals in the bag with the tater tots? It makes them all soggy, right? They didn't put those in there. That was water that was originally in the food, but it's sublimed. It couldn't go anywhere because it's in this airtight bag, and so it deposits on the bag, and you end up with all this water getting separated from the ice. And that's where freezer burn comes from, and why your food in the freezer gets really dried out and nasty after a while. And that's the advantage of the food saver bags. If you squeeze out all the air, the water has no place to sublime into, and so it just has to stay in the food. Oh yeah, I just kind of said all of that.